My calculator, and also, so we are supposed to find these values of inverse trigonometric functions using the calculator using both radian mode and degree mode. All right. So let's see. Okay, let me see the mode. Okay, it's radian mode right now. All right. So last time we finished finding an inverse tangent of 5.69. And well, we got that answer in degrees and radians as well. So for the radians, you don't have to write the word radians. I mean, even without the word, it should be understood that it is radians. How do we know, or what tells us that it's actually radians? Well, the lack of the degree symbol, right? But I mean, if you prefer to write it down as write down the word, well, that's fine. That's actually better, but you don't have to. All right, cosine inverse of negative 3/8. Well, if we go to the graphing calculator, okay, let me quit from here. Okay, let me clear all this madness here. And well, notice we have the functions, the sine, cosine, and the tangent functions. All right. Well, so we want to find the inverse cosine function by clicking the second function and then the cosine function, which highlights the function in blue, which is the inverse cosine in this case. Well, inverse cosine, just type the number. What's that? Negative 3/8. And simply click enter. Well, initially we will get the answer in radians, but we want the result also in degrees. So let me copy it and paste it, go back to the mode, to degree mode. Second quit and enter. So it's 112.02. So 112.02 degrees, or what was the other number? 1.96 radians. All right, 1.96 radians. Now let's do the same with an arc, with an inverse sign. Now notice we're using the other notation, not the -1 sort of looking like a power notation. We're looking the arc notation. It's the same, all right? I mean, this is the same as sine inverse of -0.6. Again, this -1 power doesn't mean reciprocal like x to the -1/2, like 5 to the -1/2. No, that's not what it means in this case. This is to denote inverse function. All right? Well, let's do second inverse function. Now we're going to do the sine function. And what was that? -0.06. Now, be careful because let me do this a little wrong. Let me make a mistake here. So that's -0.06, close parentheses. And I'm going to get an error syntax here when doing this using the graphing calculator. And the reason to that is that I used the wrong negative sign. So our calculator is equipped with two negative signs. So number one, the one that we have here below the multiplication and above the addition, but this is to subtract, not to have not to put a negative sign at the beginning of one expression, which is what I was supposed to be written here, what I was supposed to write here. So in this case, we're going to use the one with parentheses here, all right, and the one next to the enter and between the enter and the decimal point. So click enter, and what do we get? We get the answer. I believe this is in, okay, let me see the mode. It's in degree mode, right? Second quit, and that's a -3.44. -3.44. And now let's get the result in radians. So let me go back. Okay, it's a mode and the radian mode. Enter, second quit, and let me repeat the calculation. And we're going to get a different result, but this time using radians. And it's -0.06. Oh, by the way, I'm missing the degree symbol here. Don't know what's going on here. Okay. Degree symbol and negative 0.06 radians. All right. All right, so I mean, I guess it's very straightforward. Just calculator, second function, and select the inverse function that you want to calculate. I mean, it's not the biggest thing in the world. Now, what could be a little tricky, it's the next topic, approximating angles based on characteristics about the angle. Well, I know, so in order to be able to define these inverse trigonometric functions, inverse sine, inverse cosine, and inverse tangent, well, let's recall the whole story about these functions not being one-to-one as is, right? We needed to do some tricks of trimming their domains in a way that the horizontal line test is passed. That way we can conclude that those functions are one-to-one, and consequently they are invertible. All right. And what I'm trying to say here is, well, both the inverse sine and the inverse tangent are defined only within the interval negative pi over 2 to pi over 2, or between negative 90 degrees to 90 degrees. And the inverse cosine function is only defined between 0 and pi, or 0 and 180 degrees. However, in some applications, such as physics, for example, have any of you maybe taken physics before, or whether in high school? Well, so you might remember, some of you might remember doing this physics problem with forces diagrams, like Newton's laws, when you're trying to find the resultant force, both as a vector and as a and as a module, right? In some cases, there are forces pointing in certain directions, in directions for which we want to know that angle, that it's not defined in those quadrants. Well, we need to do some tricks so we can get those results. And in fact, for example, let's use a calculator to find the degree measure and the radian measure for the angle, but in this case, these angles will be subject to some conditions here. All right, so earlier in the previous examples, well, we just went and calculate the inverse functions using the calculator, and well, here, keeping in mind the regions where those inverse functions are defined, that is, first and fourth quadrant for inverse sine and inverse tangent, and first and second quadrant for inverse cosine or arc cosine. Well, over here, I guess we're going to break the rules in a way by doing some little trick. Number one. Okay, so let's see. What is cosine inverse of negative 8 over 11? So number one, what we want to do here is, okay, let's plot a Cartesian plane. Because we need a reference, we need a picture as a reference. Okay. Well, let me go with what's that? Okay, let me go back to degree mode, and you want to do first. You want to do this in degree, regardless of what they're asking you for, because in some cases they might ask you to just give the result in radians or give the result only in degrees. I would get both, and especially I would get the degree version first, because the degrees are easier to interpret rather than radians, or at least that's my point of view here. Well, so okay, degree mode, second quit. Let's calculate inverse cosine. Okay, so cosine theta of negative 8 over 11, it's the same as saying theta equals cosine inverse of negative 8 over 11. All right, so let's punch it in the calculator. So inverse cosine of negative 8 over 11. Okay, and let's click enter. So we're going to get 136.65 degrees. Well, it turns out that is an angle where, isn't that in the second quadrant? Okay, let's plot that angle in the second quadrant. All right, so This is the angle of 136 point what? 0.66, rounding to 2 decimal places, all right? Okay. So, oh, rounded to 1 decimal place, oh, that's 0.7. Okay, so 136.7 degrees. However, look at the condition. The condition is for us to find an angle in within 180 degrees and 270 degrees. Isn't that the third quadrant? Okay, so we are going to think of the x-axis in this case as a mirror, and I'm going to reflect this angle over here to over here, where the third quadrant is. Now, so in this case, we need to go all the way from 0 degrees. Check this out, from 0 degrees all the way to this angle. Now, how are we going to figure out this angle? So we need to add, first of all, this angle or the number of degrees for which the angle we just found is away from 180, and keep adding another, add it twice so we get this, So in other words, what we're trying to get here first is the reference angle. Remember reference angles, how those are acute angles having as a reference either the positive or the negative x-axis depending on the location of those angles. Well, that's what we're going to do. And well, 180 minus that number, so 180 minus 136.7, that equals to 43.3. All right, so this is 43.3 degrees, and this is another 43.3 degree angle, right? That means that in order to get to this angle, we're going to go from 180 plus 43.3 to get that desired angle that it's located in the third quadrant. Okay, I'm going to elaborate a little more about this. All right, okay, let me go here. So 180 plus 43.3. And that's going to give us a total of, oh no. Here it is. Yes, all right. So that's going to give us a total of, what's that? 223.3. And well, let's talk about this angle, 223.3 degrees. That's an angle way outside of the range of the inverse cosine, isn't it? Because again, the inverse cosine function is valued only between the 0 degrees or the 0 radians and the 180 degrees or pi radians. All right, that's what we needed to do in order to define it as an inverse function. And yes, we are doing inverse cosines. However, due to some applications, well, this will be applied later in your physics courses or in your mechanics, statics, or dynamics courses, in which, yes, you will still need to evaluate these inverse functions because of the directions of a force or a velocity that goes through a quadrant for which the original inverse function is not defined. Well, the trick to get that angle is by, well, doing some geometry here and adding and converting that angle and reflect it to another, to the actual, what's it called, the quadrant that we require to work on, which in this case is the third quadrant, right? Let's look at another example, another similar example. All right, what do we have here? Tangent of theta equals to -9/7. Well, let's write down its equivalent inverse trigonometric function representation. All right, so let me go over here, and this means theta equals to arc tangent of -9/7. All right. Okay, let's do the calculation using the calculator the same way we did it before. All right. So that's second tangent of negative 9/7. And let's close parentheses, click enter, and check how we get a negative angle. I mean, it's a negative 52.1 degree, negative 52.1. So let's do a negative, Cartesian plane first, and negative 52 point what? 0.1. So that's the angle, negative 52.1 degrees. I mean, which is the output corresponding to the correct domain of the inverse tangent function. Let's recall that the inverse tangent function is defined within quadrant 1 and quadrant 2. So at this point, there's no issues whatsoever. Now, there is a condition here that we need to satisfy. We need to satisfy this condition, the fact that we want an angle between pi over 2 and pi. All right, what quadrant includes those angles pi over 2 and pi? Second quadrant. That means we want an angle over here. Check this out. All right, we want this angle instead. We want to go from here all the way there. All right? Basically, a half of a rotation is required to move this angle to the second quadrant. Well, what would be the okay, again, if we do, how about we actually add 180 degrees? Doesn't that look like we should add 180 degrees? So, okay, let's see. Let's make this equal to negative 52.1 degrees. And then, well, to move it to the second quadrant, negative 52.1 at 180 degrees. And well, let's 180 degrees, actually plus, or rather minus, I mean, it's minus 52.1. So the angle is 127 degrees, all right? 127.9. All right? Well, and again, this angle clearly is not in the output or the range of the inverse tangent function, because again, its range lies only between quadrants 1 and 1. But again, this could be the result of some application in physics, maybe a resultant velocity, maybe the velocity of an airplane where we have maybe some crosswind, some downdraft, and it's an airplane going really to the north, but because of the crosswind, well, the airplane it's kind of going towards the northwest due to that. But again, since we're trying to find that angle, we need those tricks of adding 180 degrees or adding the reference angle to the 180 degrees, well, depending on the location of these angles that we're working on. All right? If we didn't have these conditions right here, well, then we're done over here. We don't have anything else to do. All right? Let's see what's next about this. Okay, so the next topic is composition of functions. Well, that's something we already did at the beginning of the semester when we defined one-to-one, before defining one-to-one functions, in order to find these inverse functions, you know. In those generalized versions of this inverse function, or rather these composition functions, in which we also define how the composition of a function and its inverse. Right? Remember how we found inverse functions, and then we evaluated the original function at its inverse, that is this statement right here, and the final result was simply x. And we did the composition the other way around, that is evaluating an inverse function at the original function, and the result was also x. This means the fact that we get this is that these functions happen to be Well, besides they are inverse of one another, well, they are symmetric to the diagonal line y equals x. Remember how we did that for the logarithmic functions? So let's see. Let me clear. Like, let me just do the ln of x very quickly. Ln of x and its inverse, which is e to the x. All right. So let's look at the graphs. Let me zoom standard 6. And well, here we can see the symmetry about the diagonal line y equals to x. Let me type it also so we can see that. That's y equals to x. And I think I'm going to do that as a dash line so we can see this as okay. And graph. All right. Well, we may not be able to see the symmetry perfectly. That's because of the aspect ratio of the graphing calculator of the screen, rather, because it's not perfectly square. But I mean, when we did this by hand, we found out that these are indeed symmetric. All right. Okay, so this is the geometric perspective of inverse function of a function and its inverse. All right. Now the algebraic perspective is that, for example, when we have a cube root function, if we cube it, the cube root gets cancelled with the cube to get x. E gets cancelled with ln x to get simply x. Ln gets cancelled with e to get x. All right. We did this as easy as that back when we covered these inverse trigonometric functions and later the relation between a logarithmic function and its inverse, which is the exponential function. All right. So it may seem like in the same natural way we could do this for sine and its inverse, or inverse sine and sine, right? I mean, why not? If it worked with the cube root, with e to the ln, with ln of e, why shouldn't it work with the inverse trigonometric functions? And it turns out that there are restrictions to them. We cannot just do this unless, for example, if we do this composition this way, like sine of sine inverse, we need to make sure that this x is a number between -1 and 1. If we have a number outside of that interval of values, then we cannot do the composition that way. All right, let's look at the first example. So the question number 1 is, can we do this? Can we just do this right away? Oh, sine of sine inverse. Oh, yes, and then that equals to 1. And in this case, we can do that because check this number right here. This 1, and since we have this composition sine of sine inverse, looking at the argument here, at the argument of the function, that's a number between -1 and 1, and well, so that's why we can do it. All right? Can we, for letter B, can we do, let's see. Let's look at the composition the other way around. Can we just do sine inverse of sine and cancel them so we get a 7 pi over 6 as a final answer? I mean, it looks natural that we can do that, right? However, we need to check the conditions here because we cannot do this unless we have this x to be a number between, or an angle between, -pi/2 and pi/2. And the question is 7 pi/6 within this interval -pi/2 to pi/2? No, it's not. Well, in this case, guys, my advice is follow the order of operations. My advice, do the inside first and then do the outermost function. I could show you another way, but I feel like it's a bit weird to do that. Well, so let's just do the one function at a time. So sine inverse. What is sine of 7 pi/6 from the unit circle? 7 pi over 6, I believe. Is that negative 1/2? Okay, sine inverse of negative 1/2. Alright? Okay, let me keep it red. Now, what is sine inverse of negative 1/2? That's the question. And again, in this case, because of this restriction here, look for an angle between or within negative pi over 2 and pi over 2. And what angle between negative pi over 2 and pi over 2 has a sine of negative 1/2? Looks like pi over 6. Okay, let's start with pi over 6. I'll take it. I'll take it. Pi over 6, okay? However, check this out. Pi over 6 is an angle in the first quadrant for which we know all trigonometric functions are positive in the first quadrant, right? However, we need an angle for which the inverse trigonometric function is negative. Negative pi over 6, all right? Do you see the trick? Do you see why we cannot just do boom boom? Yeah, 7 pi over 6 like we did here with the radicals and the logarithms. We can't do it just like that. All right? And let's see. Careful with the next composition with letter C. All right. Cosine of cosine inverse of pi. Okay, it looks like we can naturally do the following. Oh, cosine cancels the cosine inverse in the same way that cosine inverse will cancel the cosine. However, check the restrictions for this way of the composition, that is cosine of cosine inverse. Okay, what does x have to be in order to be able to do that cancellation? So we need to have x to be between negative 1 and a 1. Now the question is pi a number within negative 1 and 1? What's the value of pi, by the way? It's 3.14. Well, that's a number way outside of this range, and well, we cannot evaluate cosine inverse of negative pi because the maximum value attained by the cosine function or even the sine function is it's positive 1 or negative 1 for the minimum value. So in this case, it's undefined. And the reason to this is pi is not a number within the interval negative 1 and 1. In fact, well, its value is 3.14, so it's a number that is way outside. All right. Okay, let's keep talking about composition of functions. So what we did in the previous exercise, example number 4, well, we did compositions of trigonometric functions and their own inverses, right? However, we may and we will run into compositions of functions of different functions, not just cosine of cosine inverse, sine of sine inverse, or vice versa. No, here we have a combination of cosine and tangent inverse. And well, how do we go about this one? And they're asking us to find the exact value because, I mean, don't get me wrong, you can just punch it in the calculator and get a number, but we are required to actually use the right triangle trigonometry process to get through this result. And I know when the minute we look at this, how do we even start this without a calculator? Well, check this out. This is cosine of something, all right? Whatever this madness tangent inverse of negative 8 over 15 is, we don't care about it for now, all right? Okay, let's label this. Let's label this as cosine, let's label this as theta, all right? And I'm going to rewrite this expression like cosine of theta. That means, check this out. That means theta equals this madness right here. All right? In other words, if we write, let me write that on the side. Let me write theta equals to tangent inverse of negative 8 over 15, which means tangent theta equals to negative 8 over 15. And well, here is where the right triangle trigonometry comes into play, because here we will bring our SOHCAHTOA to construct a triangle using that information. We know the tangent function is defined as, isn't it, opposite over adjacent. Right, it's opposite over adjacent. And well, so we have a couple of options here. We can draw a triangle in the fourth quadrant, or I'm going to do it in the fourth quadrant. It really doesn't matter. So the triangle that we're going to draw here is, well, the opposite, which is a negative 8, and the adjacent, which is 15. And guess what we're going to do? We're going to use the Pythagorean theorem to find the length of the hypotenuse. That is, c squared equals a squared plus b squared. And c squared equals the quantity a, which is 15 squared, plus the quantity b squared, which is negative 8, quantity squared. Squaring both quantities here, that's a 15 squared, which is it 125, I believe? No, 225, right? 225. 225 plus 64. Add these two numbers together, and that should be 289. All right. Now, the nice thing about this is, well, here we need to solve a quadratic equation, a baby quadratic equation, by using the square root property. And I know what you might be thinking, that we need to add that plus or minus. But in this case, I'm just going to go with a positive result, because it's the hypotenuse. And well, when we're looking at points on a circle of radii r, whatever radii is, the hypotenuse represents that radius of the circle, and that's always positive. So when using the right triangle trigonometry approach, likewise the hypotenuse is always positive. The only two quantities that take positive and negative, or that could take negative values, are the lengths of the sides, and that's going to be based on the quadrant that we're working on. First quadrant, both positives. Second quadrant, x is negative, y is positive. Third quadrant, both are negative. Fourth quadrant, x positive, y negative. All right? And the square root of 289, that's a nice number actually. That's a 17. All right. With this triangle setting, we're ready to answer the question using SOHCAHTOA. What's cosine using SOHCAHTOA? Isn't that adjacent over hypotenuse? So the adjacent, which is 15 over 17. Final answer. Let's do this using the graphing calculator real quick. Show you how we get this done. Well, hopefully it works. Okay, second quit. Let me do cosine of second inverse tangent of negative, what's that, 8 over 15, close parentheses for the inverse tangent, close parentheses for the cosine, and we get a decimal number. Hopefully math, bracket, and that's our result. All right. However, on the exam, we are expected to show the process that I just showed you, this right triangle trigonometry approach, so we can incorporate this SOHCAHTOA thing and get the results, all right? So, I mean, for the homework, I guess that's fine, because for the homework you don't have to show any process, but for the exam, well, you will. All right, oh, not yet. Let's do a similar exercise. Let's do one of the same. And well, so this will be, again, let's call the quantity inside of the bracket, all this madness, call it theta. All right? So this will be, oh, not cosine, but sine this time, sine theta. And from here, we can relate this theta to be equal to all this madness here. All right? That means theta equals cosine inverse of -3/7. That means using inverse trigonometric functions, it means that cosine theta equals to -3/7. And again, let's construct a right triangle containing those dimensions. But again, careful when constructing this triangle because we need to take into consideration the definitions of the trigonometric functions. In particular, here for cosine, isn't that adjacent over hypotenuse? So that's adjacent over hypotenuse. All right, so let's go ahead and do that. And well, again, the hypotenuse is always positive, so in this case the adjacent will go towards the negative side in the x direction. So let's see. So that means -3 units and 7 units for the hypotenuse. So -3, the hypotenuse is 7. We need to find the missing side of the triangle using Pythagorean theorem again. Well, let's start with c squared equals a squared plus b squared. And well, in this case, we know the value of c because we know the length of the hypotenuse of the triangle. That is 7 squared equals to a squared. Well, a or b can be either one, but we usually substitute for a for the given or for the known length of the side. But it doesn't matter because it's addition of sides, and 3 plus 1 is the same as 1 plus 3, so it doesn't really matter. So -3 squared plus b squared. Okay, that's a 49 equals to 9 plus b squared, which results into b squared equals to 49 minus 9, which is 40, and taking the square root of 40, and again, we could take the positive. We could take the positive in this case because notice the direction of y goes up to the positive direction, and that's the square root of 4 times 10, which reduces to 2 root of 10. And you want to reduce these radicals, if possible. Notice in the previous example we got a nice perfect square. In this case, when we don't have a nice perfect square, well, break up the number into factors, and hopefully one of the factors is a perfect square and reduce it. In this case, the square root of 4, which is 2. And then let's label this as 2 root of 10. And now we're ready to evaluate what we want to evaluate, which in this case is the sine function, which, by the way, isn't that opposite over hypotenuse for sine? Okay, the opposite, which is 2 root of 10 over hypotenuse, which is 7, and we're done. All right. For the next couple of exercises, it's a similar approach. However, instead of finding inverse function or compositions of trig functions and their inverse or vice versa to get numerical values, we're going to do the same, but to obtain expressions of algebraic form. And well, we look at this and you might wonder, why do we do this? Well, that's something we're going to need later when you get to calculus 2, when you do the methods of integration, in particular the method of trigonometric substitution. Maybe you have taken calculus in high school and you have seen trigonometric substitution before, but well, you're not required to know that for what we're going to do. This is just going to be like a connection to what's going to be coming maybe in a year when you take Calc 2. All right. Well, we're going to do the same. Call this madness theta. That means sine theta. From there, we can say that this theta equals to all that quantity inside of the parentheses. So theta equals to sine inverse of the square root of x squared minus 16 divided by x. And sine theta equals to the square root of x squared minus 16 divided by x. All right, again, let's label. This is opposite because it's sine. By SOHCAHTOA, the sine function is the opposite over the hypotenuse. All right. And well, let's label. Let's draw a triangle in this case. And well, the opposite, which will be the square root of x squared minus 16, and the hypotenuse, which is just x. All right. So this one is going to be a little weird to obtain because, well, let's see. C squared equals a squared plus b squared, where the c squared is only the x, that's x squared, equals to a squared, which is one of the lengths of the side, that is the square root of x squared minus 16 plus b squared. All right? Okay, check this out. See how the radical cancels the square, leaving us with the following. Leaving us with x squared on the left equals to x squared minus 16 plus b squared. Okay, so let's solve for b squared so we can later solve for b. So number one, that's minus x squared on both sides, and see how they're going to get canceled, and plus 16 to both sides. That's going to be 16 equals to b squared, which is b equals to plus or minus 4, but well, since these are lengths of triangles, these are going to be we're just going to take the positive result, and that's going to be a 4 over here. And then now that we have all the sides of the triangle, we can answer the question. Oh, that's not sine, that's, by the way, tangent. Right? And well, by SOHCAHTOA, tangent is defined by opposite over adjacent, which will be the square root of x squared minus 16 divided by, what's that? Divided by 4. All right? So, just to give you a brief overview of what do we do in trigonometric substitution. So we solve a problem related with weird radicals for which we don't have some techniques to get that done. So we need to convert the problem in terms of trigonometric functions, solve the problem. Once we're done with the problem, we need to do the inverses of those trigonometric functions in order to get back to the original world of algebraic expressions that we had from the beginning. And there's another example. How about we do that next?